This is Ayush, and today we are going to discuss single element in a sorted array. So this question was asked by this company's in interview, as you can see the list on my screen, and this is a very important question in terms of interview as well. So let's discuss it. So uh, you're given an sorted array consisting of only integers where every element appears exactly twice, except for one element which appears exactly once. Return the single element that appears only once. So, and our constraints are like our solution must be in time O of log n, and our space should be of constant space. And our constraints are nums of length is 10 to up to 10 to power 5, and we have like non-negative integers. Okay, so let's discuss this problem through an example. What is problem trying to say? Let's switch to pad. Yeah, let's discuss the example. This example, what is problem saying? So we have a sorted array. This is a sorted array, and we are given that there is one element which does not have its duplicate, right? It is sorted, and every other element is paired up. Like you can see, one. There are two instances of one, two instances of three, two instances of four, and two instances of eight, right? Two appears only once, so we have to return it. Okay, so how do you do it? In a brute force way, that is guaranteed that at most at least one number, it is guaranteed that at least one number would occur single time. Okay, so for brute force approach, what we'll do is check each number element by element and compare the element with their next one and previous one. So for now, let's consider the zeroth element for now. So is my zeroth element equal to the next element as well? Yes, it is. So it cannot be my answer. Is my now let's move on. Is my 1 equal to the previous number or next number? Yes, it is equal to previous, so we will move on. It is not the answer. For 2, what you can see is 2 is not equal to its previous number at previous index, or 2 is not equal to the next number as well. So 2 is my answer. So I'll just return 2. Okay, and similarly we can do this for we can continue our search till we find our answer. In this case we found the 2 very easily, but what we do is basically if we are at index, let's say this ith index, what I'll do is compare I minus 1 and I plus 1. I'll check is my nums of I equal to nums of I minus 1, or my nums of I is equal to nums of I plus 1. This basically means in the sorted array we found the duplicate of the number, right? We have found the duplicate, so this nums of I cannot be my answer, right? This cannot be my answer. But in if this both cases, if this both cases do not hold, for example in this num2, right, our previous element and our next element both were not equal to 2, right? The both were not equal to 2. That's why I can say that this is a single element in our array. I'll just return it. Okay, this is the brute force. You can do this because array is sorted. You know for sure if the duplicate exists, it must exist to the next element as next element or the previous element. Okay, so now let's actually optimize this approach. What we discussed now was brute force approach, and this the brute force approach would obviously consume O of n. It is linear complexity, right? Because we are traversing each we have to in worst case traverse each element once, so this would be O of n, right? So can we optimize this? Do we have to optimize this? Yes, we can optimize this. And if you face this problem in an interview, then please tell the brute force approach first and then move on to the optimal approach. Okay, so let's discuss the optimal approach. As you have guessed it, first hint is you saw the array sorted. If array sorted, you have the hint of the binary search. You have to apply binary search somewhere. Okay, so before applying binary search, you should know how to eliminate one half, right? And you should do some case work on your, let's say, mid pointer. You should know given this mid, which half can I eliminate, right? If you are able to deduce this, if you are able to deduce this properly, you would be able to apply binary search easily. Okay, so let's do some casework. Let's see what we can explore on different indexes of mid in different cases of mid. Okay, so consider this ideal case. In this case, we don't have a single element. All elements are paired up, or every element has its duplicate with it. Okay, so what I'll do now is just look at the cases what happens. So if every element is paired up, as you can see in this array, this is the ideal case, right? So this is 1 1, this is 2 2, this is 5 5, this is 7 7. There are 8 elements in the array and each one has its equal pair. Okay, so as I said, we need to develop some cases on our binary search, on our mid specifically, to eliminate halves. So let's consider a few examples, few cases. How does mid operate and how can we eliminate halves? So let's see what happens in an ideal case. Okay, so let's consider I have my mid to be here. Okay, so mid is now odd, right? Mid index is odd, 3 is odd. So let's consider the let's divide our search space or the complete array into two halves. Okay, so let the half be two intervals be 0 to mid. Okay, and the second half, let's call it the first half, and the second half would be mid plus 1 till n minus 1. Okay, so one observation is that, can you see that all these elements are paired up, right? And my mid is now odd. So there are even number of elements in this half, in the first interval I'm talking about. Okay, mid is odd, so I have even number of elements in this half, in this first interval. Okay, so in this first interval, the pair of my nums of mid is just before it. Okay, so my mid is 3, right? So my nums of mid is 2, and the other duplicate of this is just previous element here. Okay, so in this case I'll write it down actually. So if my mid is odd here, so number of elements in first interval, this is the first interval, right, is equal to even. There are even number of elements and and if each number is paired up, then if my mid is my last element and each element is paired up, then my pair of the mid element should be just before, not after, just before it, right? As you can see from this example itself, right? So this is my mid and this is my other duplicate of the mid. Okay, so I can just say that in this case, ideally in this case, my nums of mid should be equal to my nums of mid minus 1, if mid minus 1 exists. Okay, okay, what if now you ask me mid was even. Okay, so let's consider this. So let's consider if my mid was this. Now mid is even, you can see mid has index even, and our partition is this and this. Okay, as you can see now, 1 and 1 are paired up, 2 and 2 are paired up, but this 5 is not paired up till here. So this 5 ka pair lies in the mid plus 1. So this 5 is paired up with this is mid, and this is mid plus 1. So what I'm saying is, if my mid equals to even, then there are odd number of elements in my this interval, first interval, right? So the other pair of nums of mid would definitely lie on nums of mid plus 1. Okay, this is nums of mid plus 1. So let's write it down as well. If my mid is even, number of elements in first interval are odd, so definitely I can say that my nums of mid equal to nums of mid plus 1, right? So this is the ideal case scenario. You can consider the cases yourself. And why are we doing this? We can explore through actual example, but this is the ideal case. You should understand, like, where is my mid and where should its pair lie based on the parity of mid. Now let's take the example. Let's try to build on it. How do we like eliminate and how do we do binary search on it? So that was the ideal case. Now let's consider a concrete example where basically I have a single element. In this case, we have single element as 2. We can clearly see it, right? So how do you find it using binary search? So uh, let's consider the first example. So let's initialize our low and high. Let's initialize our low to 0 and high to be equal to n minus 1, which is 9 minus 1, 8. Okay. And this is my low, this is my high, right? And what would be my mid now? This would be my mid. Okay. So now let's consider this case now. Okay. So my mid is equal to 4. Okay. I'll first check, is this the single element? Is my nums of mid single element? How do I check it? I'll check just by the same condition which we discussed earlier. That is, just write it down actually. So what is my condition what is my condition for a nums of mid to be my answer, to be my single element? If my nums of mid is not equal to nums of mid plus 1, or my nums of mid is not equal to nums of mid plus 1, this also holds and this also holds, then I can say that my nums of mid is the single element, right? The nums of mid is not equal to its previous element, nor is it equal to its next element. So I can say this is my single element and I'll just return it. So I'll just return this. Okay. So now let's check it. So is my current nums of mid, okay, wait, yeah. So is my current nums of mid not equal to its previous or next element? No. I can see that my nums of mid is equal to nums of mid minus 1. This is equal to its previous element, right? So I can just say this is not my single element. This is not my single element. I need to eliminate one half. Now let's see which half to eliminate. So this is my nums of mid, right? So, and parity of mid is even, right? As we discussed, when our mid is even, then our first interval, which was 0 to mid, this is odd. This has odd number of elements. This has five elements, which is odd. Okay. So pair of 3 must ideally lie in next element. If mid had even parity, then my pair of nums of mid should be equal to mid plus 1. In this case, mid is this and mid plus 1 is this. The 3 should lie actually here. The duplicate of 3 should ideally lie to the right of 3, right? To the mid plus 1, 1. But it is not. So can I say that this half is now ambiguous? If every pair in this half was ideal, if this half has all the pairs, then the element at mid would have its pair at mid plus 1, because parity of mid is even, but in this case it is not. So I can say that if my single element exists, which it does, we are guaranteed, so it must lie in the left half. Now it is not lying in the right half, it must lie in the left half, because left half is not good, it is ambiguous. Okay. So let's now trim down our search space, the right search space. I know for sure that my single element lies in the left half, so I'll search the left half. So to search the left half, I'll update my high pointer to be mid minus 1, which would be just high equal to 3 and high would be here, right? So let's search again. So now my mid would be this. Okay, now my mid is what? My mid is odd, right? my mid is odd, let's consider this index. In ideal case, if my mid is odd, the number of elements is even, right? So my nums of mid should be equal to nums of mid minus 1. Can I see it? In ideal case, this should happen. Is this case following? So my nums of mid is equal to my nums of mid minus 1. These are equal. So I can say, okay, my left half is good. I can surely say that left half is good. So answer does not lie here. I can eliminate this search space. I can eliminate this search space now. So to eliminate the left half, I'll update my low pointer to be mid plus 1, which is just 2. I'll update my low to be here. Okay, as these are paired up. So now let's search again. So this would be my mid now. Okay, what do we do instead of doing this? What we first do is just actually check is my nums of mid equal to my answer or not. So as you can see, my nums of mid is not equal to its previous element or next element. So I'll terminate my search and return this as answer. Okay, got it? So let's consider this example now. So this is your low, this is your high. Okay, and this would be your mid. Now let's look at the parity of mid. So before that, I'll check is my nums of mid equal to answer. Is my nums of mid equal to my answer? I'll check the previous and the next element. Yes, one of them is equal. This is equal to this. So this cannot be my answer. This cannot be my single element. So I'll have to continue my binary search. We haven't found the answer. So let's erase this. Yeah. Now let's look at the parity of mid. The parity of mid is 3. Okay. If parity of mid is odd, I can say that the previous element, the duplicate element must lie before it, the previous one, right? There are even number of elements in this compartment. So my duplicate must basically lie before. This is mid minus 1. So I am checking, is my nums of mid minus 1, is my nums of mid minus 1 equal to nums of mid? Yes, this is the case. So can I say that my left half, the left half from 0 to mid is correct, is good? All elements in this half are paired up. So I can eliminate this half. If there exists a single element, it must lie to the right of this half, because in this left half, everything is paired up. In this left half, everything is paired up. So I need to search right. So now this becomes my low, which is mid plus 1, and this becomes my high. And now I'll update the mid pointer. I'll update the mid pointer to be here, which is 5. Now as you can see that 5 is odd, right? If my nums of mid is odd, what do we do in odd case? If my nums of mid is odd, basically the number of elements in first interval are even. So the first interval which I am talking about is this, from here to here. As you can see, there are even number of elements in it, and these are paired up, but these two are not. So what we will, instead of comparing everything, what I'll do is just compare this nums of mid and nums of mid minus 1. Let's call it, right? We will compare these two, and as we can clearly see that 10 is not equal to 11. So I can see that my left half is now ambiguous. Left half is not like ideal. If there exists a single element, it is in left half. So what I'll do now is search left. As we find our left half to be ambiguous now. So to search left, what we will do is update our high pointer to be mid minus 1, which would be here, right? We'll update our high to be here, and now mid becomes this. Okay. Now let's check, is my 10 equal to my single element? Yes. As you can see now that 10 is not equal to its previous element, nor it is equal to its next element. So I can say that this 10 is my single element. I can just return it. Okay, so let's now discuss the pseudocode, like what I was talking about and how are we moving our search space and all. So firstly, in simple way, first I'll check is my mid equal to single element. If my nums of mid is not equal to my mid minus 1, nums of mid minus 1, and my nums of mid is not equal to my nums of mid plus 1, If this is the case, I can just say that my nums of mid itself is single element. I can return it. Okay, got it? If this is not the case, then we will look into parities of mid. So let's consider first case where mid is odd. If my mid is odd, I would check this. If my nums of mid is equal to nums of mid minus 1, if this is equal, then I can surely say that my left half, which is this half, is good. So single element does not lie here. So if this half is good, then single element does not lie here, and we search right. We search right in this half. Okay, if this holds. And else if this does not hold, we will go to this case if the nums of mid is not equal to this. So which means this is not the ideal case, and left half is not good, so we will search left. Okay, I know for sure if parity of mid is odd, then the duplicate of this element must lie to previous of it. If it does not hold, then I can surely say there is some ambiguity in left half and it is not good, so I'll have to search left. Single element would lie in the left half. Okay, this is the case if my mid was odd. Can we construct similar to if mid was even? Yes. So let's consider if my mid was even. So if my nums of mid was equal to nums of mid plus 1, let's write it properly. Okay, so if my nums of mid is equal to nums of mid plus 1, ideally this should hold, right? So if this holds, I can say that my left half is good. We have to search right. If nums yeah, I have explained this earlier as well. You can just rewind the video if you didn't understand why we are like taking these conditions. Okay, so if my nums of mid is equal to this, then I can say this whole left half, what is left half? I'm talking about 0 to mid plus 1, you can see, right? All elements in this half are paired, right? If all elements here are paired, then I can say that left half is good. I know that my answer does not lie in this left half. I need to search right. So we will search right here. Okay, and else if it does not hold, I can say if this condition does not hold, I can say my left half is ambiguous. All elements do not have the duplicates because I checked the parity of mid and this condition, right? So if it is ambiguous, then I know for sure it is not ideal. So if single element exists, there's only one single element, right? So if it exists, it should lie to the left. Okay, so let's talk about the edge cases now. There are actually just 2-3 edge cases. So first is if my n equal to 1, size of array is 1, just return the first element, right? If there's only one element in the array, it is bound to be single element, right? So just return it. So what is the second case? You can just check for, let's check nums of 0. When would be my nums of 0 single element? If it's not equal to my nums of 1. If it's not equal, return nums of 0. If I have something like this 1 2 2 3 3, right? So my nums of 0 is not equal to my nums of 1, so I can just say this is my single element and return it. Why we are doing this, I'll come to that. So this is my second edge case, and my third edge case would be similar to it. I'll just see in the right half, if my nums of n minus 1 is not equal to my nums of n minus 2, I'll just return nums of n minus 1. Similar to the second case, if you had something like 1 1 2 2 and 3 here, right? Now this is not equal to my previous number. Of course, we don't have to compare it to the end because end there's nothing at last, so I'll just return it. So this is my single element. So why we are doing this? We are checking this edge cases because when we perform our binary search, we must not go out of bounds. How we would go out of bounds? Because when we are like checking is it my single element or not, we are doing comparisons with mid minus 1 and mid plus 1, which can like go out of our bounds of array, right? And in the case this as well, we are checking with mid minus 1, and this case we are checking with mid plus 1, which is not like we can go out of bounds and we have to write lot of if and else more, right? So to check if we are in bounds of array. So instead of this, if you had search space something like this 1 1 2 2 3 4 4 5 5, right? This is your array. Let's say we had the search space as low and high. So instead of this, if my mid equals to this at some point, so I would have to write a if else here, right? So which is like extra code. So what I'll do instead, I have checked is my the zeroth element and the last element single element or not. If they are, I'll just stop and return it. Okay. If they are, if they are not the single element, in this case both of them are not the single element, then what I can do is just trim down my search space before even I begin my binary search. What I can do is just, okay, have my low pointer to be here. This should be my low and this should be my high. I'm saying I'm searching my single element in this in uh in this space now. So even if I compare mid minus 1 or mid plus 1, my the it would be in bounds. We won't go out of bounds. We won't have to check explicitly if we are in bounds or not. So this would be my new search space after handling these edge cases, right? So yeah, that's it. I think let's move to the code to make things more clear and to organize it properly. So let's move to the code. So let's handle the edge cases first. Let's have a size of array n to be nums.size, right? If my n equal to 1, the minimum size of array is at least 1, right? So n is equal to 1, then I can just return the first element, zeroth element itself, because it's the only element. Now if my nums of 0 is not equal to my nums of 1, then I can just return nums of 0. And similarly the other edge case, if nums of n minus 1 is not equal to nums of n minus 2, I'll just return nums of n minus 1 as my answer. So let's do binary search now. Let's initialize our low to 1 as we trim down our search space to 1 and high to be n minus 2, right? So while my low is less than equal to high, compute mid as low plus high minus low by 2. And now I'll check, is my nums of mid equal to single element? How will I do it? So if my nums of mid is not equal to nums of mid minus 1, and then my nums of mid is not equal to nums of mid plus 1, then I can say I have found my single element. Let's write it down. A single element found, just return it. Nums of mid. Okay. Now let's consider the cases of parities of mid. So if my nums of, actually if my mid is, what did we consider? If my mid is odd. So if my mid is odd, mid modulo 2, so I can check with nums of mid and nums of mid minus 1, right? So if nums of mid is equal to nums of mid minus 1, right? So I can say my left half is good. So search right. So to search right, I'll just do low equal to mid plus 1, and else my left half is not good. Left half is not good, so we will search left, which would be just high equal to mid plus 1. Okay, and let's consider the case where mid is now even. Okay, so now I'll compare nums of mid to nums of mid plus 1. If my nums of mid is equal to nums of mid plus 1, then I can say my left half is good. I'll search right. Okay, so to search right, I'll just do low equal to mid plus 1, right? And else I'll just search left left half is not good. So my single element lies in left half now. I'll search left. So my high would be mid minus. Now let's return it. Return, if we find our answer, we'll just return nums of mid here, and just placeholder return, let's return -1 because we would find our answer. We won't execute this last one. So it's running fine. Let's submit it and check. Okay, why do we have a TLE? Okay, I need to do mid -1 here. Let's check now. This should be fine. Yeah, this got accepted, and yeah, so that's it from my side. As you can see, the last our code which we have written uses a simple binary search. So we have a time complexity of log n, and where n is size of array, and we use constant space. So we have constant space. So this, our solution is in this time and space complexity, and that's it. Thank you. Bye bye.